Hi, and welcome to our first in our videos for our computer hardware class. Chapter 1 is an overview of everything and all the chapters to follow. Chapter 1 is testable material, and anything that I go over in these series of Chapter 1 videos should be taken down as notes. If you see something bold and underlined, it especially should be taken down as notes. And if you have any questions at any time, you can stop and email me if we're not in class this time, or raise your hand if we are, to clarify any points that are on there. Also, we have our class forums to ask questions as well as the online chat. So let's go ahead and get started with, let's see, okay, where we're going with what we're doing in this chapter. So in this chapter, we have three main objectives: to understand what a computer and a computer workstation are, and to talk about those parts that make up a computer workstation. Pretty simple. Some of you may already know a vast majority of the stuff we go over in Chapter 1, as it is just an introduction. Some of you may not. It doesn't matter. Hopefully we get everybody together by the end of this chapter in a similar place. So I want to start with a little background, because some of the things we talk about in this class, in the past, students said, I don't understand why we went over that kind of thing. And it's very important to me that when we go over stuff, and you'll see as we go through the chapters and the chapter list, I skip a ton of what's in the A+ hardware certification book that we're basically following because I consider it not that important. And I want to make sure that the only thing that we are getting in our class is those things that are important as far as the information is the most important information in the class. So why would we go back and talk about old computers? Because part of what we talk about in computers today relates obviously very closely to what we started out at. This is one of the original computers. And in that, on the right-hand side over there, let's see if I can point the right way. No, there's a way over there, is a vacuum tube. A vacuum tube, in its most simple terms, is a light bulb. It has two things that it knows. It's on or it's off, and that's it. And a computer, when they first started out, were made up of hundreds and thousands and hundreds of thousands of vacuum tubes. There was no other way to store data. So when we first started doing computers, we did them as a series of on and off switches represented by vacuum tubes. And my button's not going. There we go. These on-off switches are called bits. And hopefully you've heard about a bit before, but a bit is equal to what we would have said was one light in that vacuum tube computer. And each one of them can either have a 0 in that it's off and the light was off in that case, or a 1 in the case that the light was on. Now, you might say, what does that have to do with computers? Well, honestly, it has everything to do with computers, because everything in computers is done in this way. So we have a bit is just one light. 8 bits equals a byte, which is represented by this table string of data here. It's 8 lights in a row, 8 spots for data in a row that can either be 0 or 1. So each bit or byte is represented by a 0 off or a 1 on to make up an entire byte. And these bytes you can consider the letters of a computer. The language of computers is all made up of bytes, and each byte of 8 characters represents some kind of a letter. So, how many of these bytes are in a computer? Well, in some computers, there's tons. When they first came out, basically it was power and space that limited, in very many ways, how big a computer that we could make. Now, in today's computer, bits and bytes are stored on silicon chips, but they work very much the same as they did in this really old picture that you see here that I can only find in black and white, of one of the first supercomputers that did super calculations by using binary language, the language of on and off, and binary means 2, by the way. The binary language of on and off switches through the use of bytes represented by 8 vacuum tubes, and there you can see in this picture there are tons, to make a language that computer could understand. So We're going to watch a little video on how binary works in just a second, but I wanted to kind of space out this in an understanding a little further too. So if one bit is represented by a little b, okay? So that little b on here means bit. A whole byte is a big B, which equals 8 bits. And then here are some terms that we need to have. Those should be in bold and underlined. We're going to be talking about them through the entire length of the course. And if you don't understand this metric terminology of bytes, then it could get confusing later on. So if we know 1 byte equals 8 bits, a kilobyte represented by a large K and a large B, okay, large K and large B, is a kilobyte. That's 1,000 bytes. A megabyte, represented by a large M and a large B, and the B matters because M little b means megabit, M large B means like megabyte, and we're going to use both those terms later on in the course. So a megabyte is 1 million bytes. A gigabyte, represented by a GB, is 1 billion bytes. And a terabyte, represented by TB, is 1 trillion bytes. Now we're going to use kilo, mega, giga, and tera in other terms as well. So it's important that you understand kilo is 1,000, which hopefully you all remember from your basic science class. Mega is 1,000,000. It's easy to remember because they both start with M's. Mega million. Then giga is 1,000,000,000, and tera is 1,000,000,000,000. Again, those are important ones. You're going to see that on the test without question. So the reason I bring that up is because in the beginning, we were talking about thousands and hundreds of thousands of bits and bytes in a computer, and now we're talking about billions and trillions. Our servers have memory of 256 gigabytes. That's 256 billion bytes that we have stored in just one of our servers at National Trail. That's the ability to store there, just like those light bulbs. And there's no way you would ever have gotten, and let me go back to this picture, 250 billion lights in that room, right? So the nomenclature there of byte, kilobyte, megabyte, gigabyte, and terabyte is something we need to understand going forward. Okay, so as we talk about that, how does this all together? How does a computer talk and have language with just zeros and ones? And I have students ask me that every year. That doesn't make any sense. We have 26 characters in our alphabet, plus we've got uppercase and lowercase and special characters, and we've got numbers. How can a computer talk with just two things, 0 and 1? And that's what this next video is about.
Modern-day computers use electricity to work, and inside of a microchip, electricity is turned either on or off, which is represented by the symbols 1 and 0. This is called binary. You've probably heard of binary already, and that's how computers work, but do you know how binary works? Well, you're about to find out. But first, we need to understand exactly how our numerical-based system, known as decimal or base 10, works the way it does. So, there are 10, count 'em, 10 symbols that we use for all of our numbers. Starting from 0, we can count all the way up to 9 before we run out of symbols to use. Now, we could just keep adding symbols at this point, but that would get out of hand very quickly. I mean, can you imagine having to memorize a specific symbol for every single number? That's ridiculous. And that's why we reuse the same symbols over and over again in a very clever system called positional notation. So, in the base 10 system, as soon as we get to 10, or an exponent of 10, we need to add another digit to the left of our current digit. Because there are 10 symbols, each new digit has to have a value 10 times greater than the digit to its right. So that's using 10 symbols. But what if you had only 2 symbols to work with? Well then, everything that I said still applies. With just 2 symbols, each new digit needs to have a value 2 times greater than the digit to its right. So a sequence like this would equal 1 times 128, plus 1 times 16, plus 1 times 8, plus 1 times 2, plus 1, which is 155. and that's how you count in binary. It's actually really simple. It's just multiplication and addition. Now it gets a lot more complicated from here, with bits and bytes and Boolean logic and ASCII, and the list just goes on and on. So let's return to base systems. There are a lot of ways to write numbers other than decimal and binary. You've got base 2, base 3, base 4, base 5, I could go on. They all work with the same principles of positional notation. So you might be wondering, with all these numbering systems to choose from, why do we use base 10? That's a good question. This goes all the way back to Roman numerals and Egyptian hieroglyphs. It's likely that we use base 10 simply because we have 10 fingers, also known as digits. Other base systems like base 8 and base 12 are actually superior for simple everyday math, since 8 and 12 are much more easily divisible than 10. But it's definitely too late to change our minds about using base 10. We'll probably be stuck with it forever. Switching away from it now would be even harder than trying to convince America to drop the imperial system and finally switch to metric. You know, like the rest of the civilized world. Like, yeah, the metric system is superior, but who's gonna tell America what to do?
Hey, so what are we supposed to get from that? What I'm supposed to get is that computers talk in a language called binary language, and it's based on 2 digits, but it can represent every single thing that we represent with our characters today. We didn't have to have 10 numbers and 26 alphanumerics. We could have written with just 1. It would have taken a lot of paper. And in fact, if you want to learn all the characters that binary are represented by, there's books. You could Google it if you want to. You could use it as a secret code with you and your friends. But the basics is that's how computers talk with just using 0 and 1, because they convert everything to binary, or something converts everything to binary. So it goes from whatever we put in when we type into our keyboard to a binary representation of what we put into our keyboard. So when I hit the letter L, it sends the binary code of what would be L in our alphanumeric system to the computer as a binary representation. So I put on here the reason we need to understand bytes and bits and binary is to understand that the more we have available to us, the more a computer can think or compute. It's not really thinking. And I put a little symbology in there to kind of wrap your head around. Dogs have 160 million neurons that fire and turn on and off like a light, and like, and I'm far oversimplifying that, by the way. But humans have 86 billion. That's the difference between how a dog brain thinks and a human brain thinks. We have many, many times more neurons firing on our head, allowing us to do much more thinking than your common dog can do. So in terms of a computer, the amount of bytes of memory available and how fast the computer calculates all determines how big and how powerful that computer is. So understanding bytes give us a little understanding of why more is better, especially when you look at that comparison there, dogs versus humans, and how they have millions and we have billions, and that's why we can do so much more than a common household dog can do.